Hello everyone, I'm Sheida Shakeri, and today I will be presenting our research which is titled The Comparative Analysis of Thickness and Surface Topography in Mycelium Acoustic Panels. With the expansion of urban areas, noise sources increase as well, and the urban noise pollution can cause immediate and long-term health issues. So, using acoustic panels is one of the ways to deal with this noise. Unfortunately, these panels are usually made of synthetic materials that are harmful for our environment. Therefore, natural materials are being used recently as alternatives for traditional materials. So, one of these natural materials that also provides acoustic performance is mycelium. In fact, mycelium is the root part of the fungi, but it cannot be used as it is. It needs to create a rigid composite. The composites are formed by cultivating the mycelium spawn on organic substrates, such as waste paper, sawdust, hemp fibers, or so on. By growing the fungi inside a fibrous network, mycelium can act as a natural binder to attach these materials and create a mycelium-based composite that we can also call an MBC. But what are other properties of this MBC? Well, it provides acoustic absorption, it is lightweight, and it can be formed in different methods of molding, 3D printing, or subtractive manufacturing, so it can create different forms. Also, it grows on waste substrates and it's sustainable. It has a porous structure and it's biodegradable. Also, it provides thermal insulation and it is fire resistant as well. Here you can see the use of mycelium as a material in architecture. It can be used as acoustic panels, discrete and non-discrete structures, arches or facade of a building, or so on. But the main factor in the acoustic performance of a sound panel is related to its physical properties and its internal structure. Actually, the sound is affected by the thickness and the surface of the panel, but their effect changes based on the frequency of the sound. And this research focuses on this and focuses on how important are the properties of surfaces in the acoustic calculations. So, here we aim to identify the most efficient thickness and the surface topography for a mycelium panel to reach its maximum acoustic performance for an outdoor setting. To do so, first, an acoustic factor is defined to be the base of our comparisons. Here, reverberation time is selected. Actually, reverberation time is the duration required for sound to decay by 60 decibels after the source has stopped, and it is measured in seconds. Then, parametric design is integrated for the form finding of the panels. The form finding is not based on a site-specific noise data. Instead, we focused on targeting lower frequency bands that relate to the most annoying noises, which are traffic, truck engines, construction equipment, and wind rumble. And they are usually between the frequencies of 125 to 500 Hz. Then a simulation is implemented in Pachyderm software to explore the relationship between the material thickness and surface topography on the acoustic performance of the mycelium panel. And the simulation is carried out in a standard test room with the panels installed on the two opposing walls. First of all, we use the parametric design methodology through the use of Grasshopper to generate the surface of the panels. To do so, we focused on targeting lower frequency bands. So we used a Voronoi tessellation to break the geometric regularity and to prevent repetitive echo patterns. And we also generated concave, shallow, and deep parts. The depth transitions of the form was done by using a graph mapper. And the panel dimensions were fixed at 40 and 40 centimeters so that they are large enough to impact the acoustics and they are compact enough to be efficient for the mold production. Here you can see the grasshopper definition and the form of the panel as well. Then we modeled the panels with three thickness levels of 3, 6.5, and 10 centimeters, and they represent low, medium, and high material use of the panel. They all have the same dimensions of 40 and 40 centimeters, and to explore the impact of surface geometry on the acoustic performance, we generated different mycelium panel geometries of concave, convex, and the custom designed surface. Finally, the simulation is conducted in the Pachyderm software inside a standard test room setup with the dimensions of 5 and 4 and 3 meters. In fact, Pachyderm is an acoustic simulation tool that operates as a ray tracing and image source plugin for Rhino Grasshopper. The simulation emitted 1000 rays from a geodesic source to capture early and late reflections with a fixed receiver point used to evaluate reverberation behavior. The acoustic panels are placed on two opposing walls in each test scenario. Actually, 7 scenarios were simulated separately for the modeled MBC panels and an untreated test room with no acoustic panels. And the materials of the surfaces were given absorption coefficients using the Pachyderm's material editor. And here you can see the ray tracing visualization as well. And the findings of the research assessed the effectiveness of surface topography over the panel thickness. Results of the simulation indicate that all panels reduced reverberation time across all frequencies compared to the untreated room, which is shown with blue on the upper part of the graph. In fact, the untreated room consistently had higher reverberation time values that indicate prolonged echoes and poor speech intelligibility, while lower reverberation time values suggest effective sound absorption. It is observed that 3 cm panels achieve significant reverberation time reduction across all frequencies, I mean the red color, while 6.5 cm panels performed worse at mid-frequencies and 10 cm panels did not outperform thinner ones. So, increasing thickness in flat panels resulted in only modest improvements. Then, when looking at the surface topography of the panels, we realized that concave surfaces consistently performed best across all frequencies. Also, custom designed surface that we did its form finding to reach the optimum acoustic performance in the low frequencies reached its goal, and it had the lowest reverberation time value at 125 to 250 Hz. But the convex panels performed the worst among the all. So you can see the comparisons of all the 7 scenarios in the right graph. This analysis confirms that surface geometry plays a more decisive role than panel thickness in shaping acoustic performance. Therefore, among all the panels, concave panels were the most effective in reducing reverberation time across all frequencies, while the custom designed surface served better for low frequency ranges where traffic and construction noise dominates. The final outcome of this research was that the surface configuration plays a critical role compared to panel thickness in achieving the desired acoustic performance. For the future step of the research, we will build the prototype of the panel and test their acoustic performance in real conditions so that we can verify the simulation results. Thanks for listening.